I'm going to do a series of just watching Himalayan geology lectures that I'm finding. Mike Cyril, not this. These are, that's Mike Cyril. He seems to have pretty in-depth study. Pardon me. This not really related. Just looking. Okay, this one. This one I'm interested in, the South Tibetan Detachment system. I know when I was looking yesterday in my last video that it sounded of interest. I can't even remember. Also, I thought I'd just kind of take you guys on a journey with me as I research this instead of just like researching it by watching lectures and trying to find some actual data and like, because essentially how I'm feeling about this is it's kind of reminding me of how I felt that the earth expanded, where I was like, okay, I know the earth expanded, I just don't know the precise process. And then Mount Gurnar showed up, and that really brought pieces together in the process where I felt at least I could kind of overlay and the data and the observations. I just describe it, like make sense of it. Like, okay, now, okay. Then I made that video, and I mean, it's not like perfect by any means, but I believe it is a step in the actual truth, direction of truth, of the actual history of the Earth geologically. And so here, recently I've realized one of the like subtle nuances I was not aware of is that the Himalayas were caused not just by a body of water moving, but the body of water moving and pressing on the land on it, which then is essentially like layers, but within the layers there are particles that are like stable conglomerates of like a single unit that are spaced at points. And so if essentially there's a large pressure on above, it's not distributed evenly, even though it's distributed evenly on the surface. The layer then redistributes it into the single largest particle that was under the region of what would become Tibet. And this supernovaed in a legitimate way, where we then saw a mountain chain created as a result of it. And so that line of reasoning, I feel highly likely to be true. That's how the mountain chain formed, was a literal supernova of a particle that was experiencing pressure from water above, which then caused it to cave in and explode outward away from the direction that the water was going. So like in the direction the water was going, with the direction of the water towards southward, creating an arc. So that's where I'm at. And so we're just gonna go ahead and like see what evidence people are talking about in these more technical types of settings. So this is Don Kellett, the South Tibetan Detachment System. 30 minutes. They're all like an hour and a half at the most, which is pretty good. Okay.
Hello, my name is Dawn Kellett, and I'm a research scientist at the Geological Survey of Canada. I'm grateful for the invitation from the Tech Task team to give a lecture on the South Tibetan Detachment System, a major structure in the Himalayan origin. This is an outline of what I'll cover over the next 40 minutes or so. First, I'll give a brief introduction to the Himalayan origin, and then I'm going to discuss why it was so surprising to discover a low-angle, origin-parallel normal fault in this tectonic setting. Then we'll dive into the South Tibetan Detachment System. I'll review its discovery, look at a few classic exposures across the origin, and then we'll look at some of its structural and metamorphic characteristics.
I'm just thinking, so before I go on, let me just pull this up. Let's get rid of labels. Okay. It occurred to me. So initially I was thinking, essentially, not to use Mount Grenard as a basis, but just imagine the particles here. It explodes and it creates the Himalayas. So I was thinking it should have perhaps an upward art, an upslope, a slope of material moving in from a lower elevation over here at where the particle was to a higher elevation where the Himalayas are, creating perhaps where what she's saying, this low angle parallel normal fault. I'm not sure what this is about though. So I had that thought, but I do believe that yesterday I ran into what sounded like that the angle is sloping from the north to the south, so it's actually the opposite. It's kind of more like Gurnar, like here, but like a fault line that's sloping downward, which doesn't really make sense if it's a supernova that's radiating energy that then generally goes upward and then ramps out of, like, goes upward slope and then kind of maybe ramps out it when it reaches the surface area for some reason. I don't know why it would ramp out, but maybe because of hitting, maybe it's just going forward and then it runs into the Indian resistance of the Craton of India, which perhaps there is some type of like boundary between India and Asia. It's just that boundary is more like how there's boundaries everywhere. Like there's boundaries within. And sometimes the energy flow propagating through the boundaries is enough to physically sever the connection between the systems and have a new system like in between. So, um, one potential, depending on what we're seeing before I move on, why I was saying this is there's this fault here, like the energy propagates out through these ridges in Mount Gurnar, seemingly, like as Mount Gurnar is being emitted from the earth by basically ether flows pulling energy, pulling matter with it and shaping it and separating it into Mount Grenard's like unique geological conditions where it's a literal crystal, first of all, besides the point. But the energy then here, it flows out to this second system here, and then it literally creates a boundary between the two where the second system like severs away by like an umbilical cord being literally severed away. It's separate. This here, I've never looked at this before. Specifically, what I'm about to say is interesting. How this kind of goes out to the second system. The second system here, I've never noticed this, has a spiral to it. It totally has a spiral to it. Oh my god, it has a spiral to it. This here, this here. Ugh. Oh my god. How did I not notice that? It spirals around here, and here, here, here. Second system has a spiral. Cool. So that's a new WoW recording, like in the moment realization. Maybe it's not about the Himalayas and something I'm more acquainted with, although still not remotely acquainted with, obviously, but enough to feel I'm more acquainted with. But anyway, let's move on. I'm just kind of setting up my thought process for why whatever might be said, I might like lean in a direction and consider that avenue or that avenue. So we'll see. Hopefully it fits in and doesn't shatter my hopes. It's just like, wait, everything I thought I knew was wrong, but I was so careful.
In detail. Then we'll look at some of the other major aspects of the detachment system.
That's life, I guess, huh?
It's a cross-strike extent, the role of partial melt, how the structure fits into the evolution of the origin. And then I'll wrap up with some outstanding questions that we're just beginning to pick away at, and some future potential directions of research. The photograph on this slide is looking westward at
partial melt thermal evolution. I do like that there is a lot of heat present because it was a supernova.
Planet, and the South Tibetan Detachment system cuts right through it. Okay, first we'll take a look at the Himalayan origin. During the Cretaceous...
Origin. It just sounds too much like origin. So I say like orogeny. So I never know how to say it. Or I think origin is the actual pronunciation, and then orogeny when there's a Y. I like the orogeny word. I don't like origin. I think it sounds like it has an I. But it doesn't sound right. Orogen, like without the Y to say it like that. But I really like orogeny over originy. I'm not sure about that.
The Indian Craton was far
The life of someone sitting in a bedroom researching
south of the Eurasian plate, with an expanse of ocean floor separating them. As India marched towards Eurasia, that ocean floor was progressively subducted beneath Eurasia, forming an Andean margin, today exposed as the Ganges batholith. Once all that ocean floor between India and Asia had subducted, continental collision began, forming the Himalayan orogenic belt. You can see the topographic expression of this collision in the digital elevation map in the top right of this slide. The Indian Craton...
I gotta make sure I remember Mount Gurnar second system. I just call it the second system. Spiral. Maybe I will even come here. Open up my snippets. Right there, I guess. Save as snippets, Garnar. Spiral second system. I think it's like data or per or something. I'm not sure. Something of that nature. Maybe I'll even, before I leave snippets, give it a pretty poorly traced tracing. It's hard to trace by mouse. This even has, I wonder if these are like 90 degrees here. Seems maybe there, and maybe also that way. I mean, it's generally there. It's like an ammonite. It's like an ammonite. Highlighted. Okay. And then do this.
is low-lying and has low relief. And forms an arc of high elevation and relief. And beyond
Oh my
it, to the
god.
north, is the Tibetan Plateau,
I was
buttressed to the
muted
far north.
because, yeah, sounds. Parents were talking. And I forgot to unmute. That's why I can't fucking mute. Sorry. I don't know what I just said that whole time. How long that was. A couple minutes. Not too long, but long enough to be probably like, what the fuck, dude? It's probably like 3 minutes.
By the Charon Basin.
It is what it is. I don't know. I literally. Oh, yeah, I was talking about Mount Grenard. Mount Grenard. I just. Yeah, so this is Spiral. I don't know if I got that on. I mean, obviously, if you watched it and were like, what's he saying? I don't know, but I can see what he's doing. Alright, let's move on. It doesn't matter. Himalayas.
This is a lithotectonic map of the Himalayan orogenic arc. You can see it has been separated into relatively few units with pretty impressive along strike continuity. Although there is greater complexity lithologically than what's shown in this map, the origin is remarkable for its along strike consistency in both structure and rock types.
Perpendicular extension. So just elevation. Initial collision. So the explosion happened. It started to run into this region initially. This explosion was, I believe, the one that caused the chain reaction, I guess, of Chicxulub and all, just the world to supernovas. It was a global supernova where the crust was able to fully sever to a point where new oceanic crust could really fill in before it was still too bonded to fill in the gaps as much. Just real quick. Oceanic crustal age. So all the yellow and red and orange, like pretty much yellow maybe was there somewhat around the edge, but the red and orange all occurred after the supernova. And maybe a little bit of the yellow, it looks like, just not the whole of the yellow. So, like, all of this was added when the bonds between the continental land masses were severed. And then in rushes the oceanic crust. But that was 66 million years. That was Chicxulub, Deccan Traps, Shiva crater, Nader crater, Baltish crater somewhere over there. Happened at the same time, some reason. A bunch of things happening simultaneously. Mount Gurnar formed in 65 million years, apparently, something in that region. It's just a bunch of things. Also, what was it? I think some biological thing that was at 65 million years ish. That was like, but I don't know.
To look at the structure, we can take a representative simplified cross-section in the vicinity of Mount Everest, that black line on the map. In cross-section, shown below, the orogeny comprises 4 main north-dipping structures.
So a collision is like the energy, the material hitting and causing, I guess, some kind of separations, metamorphism in the heat of it all, high temperature metamorphism. I don't know what mid-cross means exactly. If that's like mid this way or mid like down. Let's see. I don't know. So, okay, there's the Indian plate. Okay, look at that. It is in fact sloped from the direction of the supernova. And so is all of this generally sloped from the direction of the supernova, ramping off of the resistance, going in an upward direction, which also happened on Earth when the Earth was fracturing. It's a little different, but it's similar because essentially the crust was fracturing down from the Mediterranean. Then I think it went this way actually. Came across here. Some reason, based on some things I was seeing. I'm not sure. Not to suggest that it's more pointing at Flemish Cap, but I think there was some evidence that it went this way. But either way, if it went this way, it came to generally, let's say it came through here, and it came across, and then some reason it just suddenly goes this way. It doesn't actually keep going. It goes as if it hits a wall because these are still together. South America and Africa. So when the energy propagating down here hits where South America caused resistance because there was a craton there, I guess, like this craton here that's like physically outlined, especially here. It hits it here, and it just literally gets sent off perpendicularly, ramps away the energy, even maybe it literally ramped, like with this shape here, like ramped into, turned, the propagating wave just turned and came this way instead, like it's kind of like the supernova moving energy down some line until it hits the Indian craton and then is caused to ramp either down, but it went up because of its trajectory was upward. If it had been going the other way, it would have went down. But because it was from below the Earth's surface, it had a generally upward trajectory. The segment that was traveling there, causing literally the Himalayas to ramp up out of the collision with a large amount of heat in the process, it seems, causing metamorphism not just below the surface, but even like of the sediments in the region. Maybe.
The main central thrust, boundary thrust, and main frontal thrust are all south-verging thrusts that root into the basal detachment of the origin, the main Himalayan thrust, with the main central thrust being the oldest and the main frontal thrust the youngest. The South Tibetan Detachment.
Wait, say that again? Pardon me.
With the main central thrust being the oldest and the main frontal thrust the youngest.
Thrust. That's just a fault line. This is the original, and then the youngest. That kind of makes sense. I could see that. It would be like insufficient. It's insufficiently deflecting the energy here by this resistance that it was experiencing, and so the energy continues to carve into it further. I wonder if this is just like ether transforming particles in ways that I don't understand really, to a point where like it doesn't even need to actually bring material, although that doesn't make sense. I think it's literally bringing this material, and the ether is what's like the lubricant bringing it through. Is this like just ether energy, gas that's beyond gas? It's just like it causes space in abundance. It creates voids in abundance that allow for just free flow with no resistance of materials when it's surrounded by ether, because there was a bunch of ether that was physically flowing through the particles, around the particles, due to the supernova of a particle up in up here region that then sent a wave.
The South Tibetan Detachment System is the hinterlandmost of these structures. It's also north dipping, but it has a normal sense of displacement. Like the others, it's an origin parallel structure, and its present-day dip at the surface is generally less than about 30 degrees.
I gotta go back again. I'm just too busy talking and not actually listening.
There's 4 main north dipping structures. The main central thrust, boundary thrust, and main frontal thrust are all south-verging thrusts that root into the basal detachment of the origin, the main Himalayan thrust, with the main central thrust being the oldest and the main frontal thrust the youngest. The South Tibetan.
So these thrusts are connected to this thrust, where this one is not connected.
The Tibetan Detachment System is the hinterlandmost of these structures. It's also north dipping, but it has a normal sense of displacement. Like the others, it's an origin parallel structure, and its present-day dip at the surface is generally less than about 30 degrees. In its hanging wall, the blue unit, are sedimentary rocks of the Tethyan sedimentary sequence.
Less than 30 degrees.
And in the footwall, in pink, are the high-grade metamorphic rocks of the greater Himalayan sequence. Those red blobs right underneath the detachment signify plutons that I'll talk about again later in the talk.
Plutons, yeah. intrusions.
On the right, I've listed some of the important timestamps of the orogen's history. Collision occurred in the Eocene, and then burial metamorphism of that
It would
pink
kind of
unit
make sense
followed,
that
that highly
it's,
metamorphosed.
let's say that there's a particle of supernovas and it literally brings intrusions of some particles, like big particles, just that are then literally speckled throughout the chain, especially near the center point, it seems, or more detectably near the center of the wave, because this is the center of the wave. It's very important to know. Even though the Himalayas are said to only be here, that this is definitely all one system, all correlated, and to ignore this aspect is to not recognize it. It basically makes the center more here, because if we think of it as here, like the center then becomes more like here. This is more the center of the what is known as the Himalayas, but it's not the center of this whole land feature, which is why I don't like the name of the the Himalayas definitely need some adjustment in our analysis by incorporating more features around it into part of its process for decoding how it occurred. Like this needs to be part of the Himalayas in our analysis of the Himalayas, or at least like its relationship well established. Something needs to happen with anyway. Like I don't even know what this is. Like it's literally so hard to find like a name for this. It has a name, I know, and I just don't think it's like consistent. It's just not, even though it's literally is part of the Himalayas. Just crazy. It's like the unknown, the forgotten Himalayas. Okay. This is interesting. I wonder if this is like tabs forming, like a bond forming between this like atom, this nucleus, this particle forming a physical bond across the barrier of another plate, this unit, this slab, this another atom basically, that maybe instead of just like facing resistance like here, instead there was sufficient energy in this region to create a bond between the two like slabs of land. 'Cause I was just noticing how this is kind of flat. It almost suggests like a bond occurring. That's pretty crazy. What the the like way the Himalayas are shaped. Oh my god. They do kind of look like the dendrites of shallograms. The explosive parts, like if you look at shallograms, where they have the spiral, like this, but where it has intrusions, if you will, of some sort of overlaying material that is then dendritic in nature, and the gold looks gold. The golden material, when it overlays through a crack like that, will produce. Here's some this kind of dendrite-y. going on, but that's not where I'm referring to specifically. Like in there, maybe. Maybe like that, but more on the outside of these. Like this, I think this is the one. Maybe not. Crazy. Crazy. This is like this. Layers with a particle between where the energy flowed between the layers, and it stripped out the less dense material around it, creating this actual layering structure in this rock just literally naturally. Oh my god. I'm trying to find it. I should have just looked through the images. I was just thinking I'd find more. That kind of has it. I mean, this has it on the surface, but I'm thinking of something else still. This kind of low. This is Himalayan, like, nature to what's happening. Like, just the way the snow-capped mountains are. Essentially, those are where the currents flowed the most in the mountain building process. Like down here, there wasn't as much current. Why wasn't there as much current? Because the flows that were building this were literally the same variety as this type of structure, where there's a actual physics of a lightning energy, but not even lightning, ether lightning kind of thing that's travels through the earth in specific weak points and then produces everything we see, all these features. Like here's kind of, maybe this is the one. Oh, there's a particle supernovaing, shoving debris out. So like to the point where the shoved debris penetrates the outer shell of the crust of the shallogram of the earth and literally creates a mountain chain, where within that mountain chain, I will find it. There's maybe a little bit there. This is incredible. There's probably some of this going on. I know I found some that's plausible here around here where the shallograms are from. This looks like maybe there is a double, like a pair, two lines that are just too, like, not everywhere else. Like that kind of thing is not quite what's going on like here. There's not a separation with two like parallel little stretches that aren't really like anything around them even. It's not, I haven't looked that closely, but I don't see, like in here, I don't really see necessarily anything quite of that nature. Like maybe, but it's for sure though. I see dendrite structures that are common in shallograms. It's probably like the last one. I mean, this one might have it enough. Like, how ridiculous. Where is it? Oh my god. One of them has the gold, this is this one. There it is. There. And it's got the little dendrites. That's what I'm kind of thinking with that. So let's go back here. The main frontal thrust.
Greater Himalayan sequence in and around 35 million years ago. In the early Miocene, there was a high temperature metamorphic event, and then during the late Miocene, origin perpendicular extensional structures were formed across the belt. Now that we've established that the South Tibetan Detachment System is low angle and it's origin parallel and it has a normal sense of displacement.
It doesn't even actually make sense. A low angle collision of plates. They're basically suggesting that plates can have borders that have really low angle slopes. Like they almost have to be 90 degrees, like perpendicular to even make any damn sense. Like it doesn't, like they have to be kind of like like they can't be like, it doesn't really make sense that the plate would have this just slow slope that's just going on. I mean, I guess if it just goes under that far, maybe it could create a slope like that, is the thought.
Displacement. Let's discuss why that is so surprising in this tectonic setting. If you recall Anderson's theory of fault dynamics shown here at the bottom of the slide, and the Moore Coulomb failure criteria shown at the top, we expect that faults will form at an angle of about 30 degrees from the maximum principal stress axis, sigma 1. In a plate collisional setting, we expect that sigma 1 is in the plane of the Earth's surface and oriented parallel to that collision direction. Depending on the gravitational loading in different parts of the origin, we might expect either sigma 2 or sigma 3 to be perpendicular to the Earth's surface. So in an orthogonal collision like the India-Asia collision, we expect to form origin parallel thrusts or strike slip faults, which does describe the vast majority of structures that have formed in the Himalayan origin and the adjacent Tibetan plateau. Even in the case that sigma 1 was locally perpendicular to the Earth's surface, we would still expect that any normal faults that formed would be perpendicular to the origin strike and to form at relatively high angle, or about a 60-degree dip. In this framework, forming an origin parallel normal fault, like the South Tibetan Detachment System, seems to imply that the minimum principal stress axis was oriented parallel to the collision direction. Low-angle normal faults are relatively well known in other tectonic environments.
That seems really important. I just do not understand this image very well. Basically, it doesn't make any sense to geologists, to the general traditional geological interpretation, like the way that it is. I can glean that, but I really cannot actually grab it to then reiterate it as a point. Like, we don't actually, like, it's well established in the geological community that this doesn't make any sense. So, like, we're trying to explain it by this, that, and the other way. But essentially, that it needs an explanation, and our models can't explain it. I can glean that, I just can't reiterate it very well at all, pretty much. The angle of thrust doesn't make sense because of something.
Origin parallel normal fault, like the South Tibetan Detachment System, seems to imply that the minimum principal stress axis was oriented parallel to the collision direction.
Minimum? I see, I don't know. stress vertical. Crustal compression was oriented this way. I guess is what she was saying. Instead of
Low-angle normal faults are relatively well known in other tectonic environments, in extensional provinces like the Basin and Range in the US, in metamorphic core complexes,
which was added due to the expansion of the Earth, I'm pretty sure. If she's talking about West United States, Western, like Utah kind of area.
like this example also from the southwestern USA, and at mid-ocean spreading ridges. However, these are generally extensional, not.
Which is interesting. I guess that's how it adds on. Generally extensional provinces, meaning just accretions. I guess accretions. This kind of makes sense for accretions.
Contractional settings. Even in these settings, there has been a lot of debate about how they formed. For example, did they really form as low-angle detachments, or did they rotate into low angle subsequent to their formation? Of course,
I don't quite understand. Ooh, Kaligandaki Valley. Nice.
structures have formed in the Himalaya, like the Tukola Graben in the Kaligandaki Valley in central Nepal, which you can see in that Landsat image in the top right. So the one structure in the Himalayan origin that doesn't.
It's like it divides. So like I talked about this in a previous video where this ammonite here has these circles that I believe are just like the structure of the spiral causing this is not able to maintain the shape of the ammonite here, and for whatever reason broke down and kind of just started to create bubbles of, but the bubbles didn't actually go out uniformly. The bubbles actually have this gap here. There's a little gap here where they're not really, like, why aren't they there? And it's almost like they separate, like half here, half here. As they came out, they started to separate into different streams that maybe if there were more, would be more, even a bigger gap here without filling in. So that kind of makes me think of like the concept that like energy likes to divide into segments, and then in so dividing, it basically creates a actual separation and combine. But when it divides, it can show manifestations of division in the terrain where what I believe maybe, like I was saying, like maybe this section, like if we just arbitrarily say measure distance here, drag, 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 drag. Okay, so they're about 1,500 miles, 2,400 kilometers. Okay, so let's try from right here, clear measurement, measure distance to this division, and let's see if this is about halfway between the two. It's pretty damn halfway. So it's almost like the energy that was flowing this way divided physically, and this is a manifestation of the division of the energy. It's not like so substantial, but then as to like create a huge gap, like there's not like a break in the Himalayas really, but there is a break in the Himalayas. But it's not the only one either. These things seem to be at what may be like divisions of the Himalayan mountain chain, and maybe even also correlate to when it's a whole versus divided here. Although this makes it suggestive that this, in some energetic sense, is the totality of the Himalayas, and this region is some energetic sense separated, and maybe that's why there's enough like variation for them not to be really considered part of the same formation. Although it is convenient because then it's easier to explain, to separate them, be like the Himalayas are caused by India and these are unrelated. Boom. It seems you just kind of like cut out the mountains that are literally connected. Okay. I wonder though, I was just thinking, this measure again, clear measurements to here, I got 600. But if I were to actually try to follow the outline a bit to like here, maybe to make it 700. I mean, it's maybe it's like a third-ish, not completely, but like 1, 2, 3. I don't know why that would matter, especially. This really does look like dendrites. Just branching from the north to the south, meaning the energy propagated from the north to the south, creating these dendrites. And then there's even interlocking low elevation dendrites, kind of like that one shallogram. Oh, this one's easy to recognize. It's just this one. Kind of like this, interlocking, but the interlocking one is even... this one's... They're kind of the same elevation looking on this, but they do interlock, which alone, coupled with that they're dendritic structures, probably suggestive that there is something to the interlockingness of this from both sides, not just that they look like dendrites this way. Although it may just be that the interlockingness is that they overlap, but that doesn't really, like, this looks like a dendrite in and of itself, where like it requires many dendrites to shape it into being itself a dendrite, so it must itself be one. It's kind of my thoughts. Okay, let's carry on, because she was talking about here.
Doesn't fit that classical fault model is the South Tibetan Detachment system. And it's not a local structure, but one of the major faults of the origin that extends for over 2,000 kilometers of strike length. Fit that classical fault model is the South Tibetan Detachment system. And it's not a local structure, but one of the major faults of the origin that extends for over 2,000 kilometers of strike length.
So it's like right down the middle too. And then we got the Greater Himalayan, so it's it's leading up to where the highest peaks are, which is generally down this middle segment, I think, in the pink. especially maybe even exactly in the pink and red, like a combo of the pink and red. That is Mount Everest right there, it says. So maybe the red adds some elevation, but by being like an intrusion of some material that penetrates into the rest by being literally debris, a larger debris from the supernova, something of that nature, like blobs, just based on this.
So let's take a look at how the structure was first identified. These two cross-sections are from a well-known contribution on Himalayan geology by Patrick Lithot in 1975, covering the structure and geology of the Himalayan origin. And it's perhaps the last major contribution which doesn't show a South Tibetan detachment system. These cross-sections are both from central Nepal. You can see Dhaulagiri Mountain in the upper section and Annapurna 1 in the lower section. And on the left side of the cross-section, you can see the main central thrust plotted and the metamorphic rocks of the greater Himalayan sequence above that thrust grade up section into folded strata of the Tethyan sedimentary sequence, so a gradational contact. This was the prevailing understanding of the greater Himalayan sequence, Tethyan sedimentary sequence contact at this point in time. However, less than 10 years later, Jean-Pierre Berg and colleagues published the first characterization of a shear zone at the top of a metamorphic package, at the top of the metamorphic package of the greater Himalayan sequence that showed a top down to the north, or normal, shear sense. The map above shows the area that they were working between Lhasa and Nyalem in southernmost Tibetan China. And they show the shear zone separating migmatite and leucogranite injected metamorphic rocks in the cross-section below from, at the far right, above that normal fault, unmetamorphosed sedimentary rocks. This work is what we commonly recognize as the first to discover the detachment system, although there has been mention of a normal fault in the Manaslu area by Japanese researchers back in the 1970s. Less than 10 years later, again, in 1992, two pivotal papers were published by researchers at MIT. In the top diagram, you can see those black lines represent 6 transects this group mapped, covering more than 700 kilometers of origin strike length from central Nepal in the west to Bhutan in the east, in which they convincingly demonstrated that the South Tibetan Detachment System is an origin scale structure. The bottom half of the slide shows the title of the science paper they published in the same year on an age determination for the shear zone. The result coincided in age, about 21 million years, with timing constraints on the structurally lower and opposing sense of shear, main central thrust. The implication is that not only did the detachment system form in a collisional setting, but it was active at the same time as a major parallel thrust. Okay, so now let's take a look at the detachment system by visiting a few of its classic and best-known exposures. First of all, I'll remind you of its bounding units. The hanging wall of the detachment system comprises a suite of Paleozoic to Mesozoic sedimentary rocks that were deposited on the passive northern margin of the Indian plate as it marched north towards Eurasia. The sediments were deformed in the India-Asia collision into a south-verging fold and thrust belt.
Sorry, I was muted because my parents are talking. But it looks like this is the north, this is the south. Okay, good, that's good. Because this said North Himalayan Fault Zone, so I was a little confused. Thinking maybe this was the north, this was south, but this is further south. This is further north. Okay, And so from the north, there's a consistent like propagation from below to a resistance where they then start to begin to rise. This matches the supernova so far.
which is illustrated in...
I honestly didn't know this. See? Beforehand, I was like, I thought it was going this way and it would be like counter and it wouldn't really make sense unless it was like kind of like pushing layers in front of it, causing a fault line in that way. But in this way, it makes much more sense. This way is the easy way to explain. So, good.
cross section here beautifully by Lithot Rajbashar and colleagues. The footwall to the detachment system is a suite of highly deformed and metamorphosed Neoproterozoic to Paleozoic, metasedimentary, and metaigneous rocks, which was perhaps also deposited on that passive northern margin of the Indian subcontinent. Partial melting during metamorphism has also produced migmatite within this package, and there's been pooling of melt into fairly large volume plutons, such as Manaslu. Okay, so we'll start our tour in the Zanskar region in the western Himalaya and make our way east, stopping in central Nepal and then reaching the Everest region. This cross-section depiction of the Zanskar shear zone is excellent because it shows all the main elements that we see again and again across the orogeny. The migmatitic footwall, which you see to the left, here called HHCS, or Higher Himalayan Crystalline Series, that's what I've been calling the Greater Himalayan Sequence, is pervasively deformed, and melt derived from it feeds an injection or intrusion complex that sits right at the base of the detachment, with some dikes being deformed in the shear zone. The Zanskar shear zone, a local name for the South Tibetan Detachment, itself is about 1 kilometer thick and preserves a condensed upright metamorphic field gradient, above which is a sharper detachment structure. The rocks above that structure have a distinctly lower metamorphic grade and also a different structural style, and that's the Tethyan sedimentary sequence. Moving to Dhaulagiri in central Nepal, you can see some of those same elements in this cross-section by Mike Searle. Above is a photo of the ridgeline of the region, and then that interpreted in the cross-section below. Again, the metamorphic rocks above the main central thrust, which is in the far left.
It literally separated them just like it did at Mount Gurnar. But this time just by a burst of energy in a direction passing through a medium separated the materials.
Of the cross-section are pervasively deformed. The South Tibetan Detachment System lies above this in about the yellow unit. Here we don't see an injection complex, and above the top of that detachment system are the Tethyan sedimentary series rocks with their distinct structural style and lower metamorphic grade. And then we move on to the Everest region, and here you can see the detachment system spectacularly cutting through the top of Mount Everest, or Chomolungma. I'm showing two cross-sections here, and north is in opposing directions, so a bit confusing. North is the center of the slide for both sections. Here again, we see a ductal shear zone with an injection complex, and at the top of that, a discrete brittle ductal detachment, above which, at the very peak of Everest, are low-grade sedimentary rocks. The local names for the structures in the Everest region are the Lhotse shear zone and the Chomolungma detachment. To the south, and I've indicated the structural elements on the mountain. And we'll take one more shimmy east to the Dingya region, and in this cross-section, the view is to the north. So you can see in the right corner the upper detachment surface of the South Tibetan Detachment, below which is a kilometer-thick top to the north shear zone with injection complex. Here you can also see the relationship between...
Are they talking? That must be those ones. Well, they look kind of like they might be generally perpendicular, which would make kind of sense. That would make sense if they're generally perpendicular.
in the detachment system and those late origin perpendicular high-angle normal faults that cut and postdate the South Tibetan Detachment system.
The reason that would make sense is that seems to be common, where there's some sort of perpendicular aspect. This ridge comes in, and then this fault line is at a perpendicular angle. I may not be cheating to make it exactly 90, but it's, I've shown this before. There's lots of 90 degrees. These ridges are 90 degrees. Also, if I get that one and this one, something like that. And then also this one. And this one. This is 120 to... It's 120 to here, and then it's 90 to here. Obviously, at some point, it's because of energy flows. What exactly is going on, I can't say yet. I don't know. But...
So we've traveled across the origin and we've seen several common elements in this detachment system. There's often an upper discrete detachment plane, and underlying this, there's about a kilometer-thick ductal shear zone within high-grade gneiss and schist, as well as leucogranite bodies, which in places form significant syndeformational injection complexes. Now we'll look in detail at the structural and metamorphic history of the ductal shear zone. Here I'm showing some outcrop photos from the South Tibetan Detachment system. The photos on the left have been flipped to keep the cardinal directions consistent with north to the left. The migmatite on the left show asymmetric sigmoclasts and shear bands with top to the north shear sense. On the right, you can also clearly see the shear sense of the deformation and the relationship between in situ melt and dikes and the deformation. This relationship between melt and deformation is
north, south, north, south. They're all going top to the north. I don't understand the phrase then, I guess. I thought top to the north meant top, like the higher of the two sides was on the northern side. I don't know. This looks like it. Oh my god.
important not only as a tool for dating shear zone deformation, but also for understanding the rheology of the system during flip. If we zoom in further to the thin section scale, we can see the relationship between metamorphism and deformation. Here we see thin sections of two different metapelites with SC fabric preserving the shear sense. In general, the fabric wraps around peak metamorphic phases such as...
What if it's like a tide, there's a first out along that angle, but then it comes back, like a degree of the energy basically is brought back through the same avenue, creating slips in the opposite direction also, but the same angles generally, because this is south, north, 30 degrees, like exactly.
It's garnet, but we can also see sillimanite growth in that lower image growing along shear bands, indicating that Shear was accompanied by fairly high temperatures. Here I'm showing a few more thin sections that illustrate the relationship between metamorphism and deformation. And in the bottom left, there's also a backscattered electron image of a garnet grain with, in bright white, monazite inclusions. By dating accessory minerals like monazite in situ within rock slides, we can put timestamps on prograde, peak, and retrograde metamorphism.
I love that one of the rocks is called City Man Night. City Man Night. Every time I look at it and I'm sitting here thinking I'm all profound or having some deep moment, like, okay, City Man Night. Oh yeah.
In the top left, I've plotted two different examples of that, two different pressure, temperature, time paths for tectonites from different segments of the Ductal Detachment shear zone, one from the Everest region and one from Bhutan. The small numbers represent MA, millions of years ago. You can see that those paths are different, but both of them show fairly open pressure, temperature, time loops, with pressure decreasing upwards on the y-axis. If we look at the metamorphic grade right through a structural section of the detachment system, here's a compilation of the peak metamorphic and deformation temperature through a few different segments of the South Tibetan Detachment shear zone. The RSCM is Raman spectroscopy of carbonaceous material. This is a useful thermometer for relatively low-grade metamorphic rocks. What we're seeing here is a quantification of the earlier observation that you may have made on the Zanskar shear zone, that the shear zone preserves a condensed, upright metamorphic field gradient. The metamorphic grade decreases sharply across that kilometer-thick shear zone. Here, the field gradient is on the order of 375 degrees Celsius per kilometer. Other recent studies have reported between 200 and 300 degrees Celsius per kilometer.
Structural distance above base of the South Tibetan Detachment System ductile shear zone. So below the shear zone, the temperature is constant. I'll be right back. Freaking little ants. Let it out instead of smashing it to oblivion.
This field gradient
Sorry not to laugh, because I never know what the future holds.
is not just a product of simple shear. Many researchers have shown that the shear zone also underwent significant pure shear during slip. It has been flattened.
But this is interesting. Is this saying? I'm not sure if this is saying that as we approach above the shear zone, we see significantly lower temperatures, peak metamorphic deformation. So, like, the shear zone was produced due to the flow of energy creating a shear zone. Not really literally being part of the flow, but it was influenced by it because the further away above the base, apparently, the less heat that was in it. Like, it's strongly suggestive that it was receiving the heat from an adjacent current flow that was then, like, passing into it, but not able to reach as high above it to transform the rocks as much. That kind of makes sense to me. Assuming that's what they said. that's what was being said by that. I think it was, but I'm not sure.
Now that we've taken a close look,
Keep reading, listening, watching, whatever the word is. All of the aboves. I just feel like I just feel judged reading. You're watching a YouTube video. You fake ass.
look at the detachment system, right to the thin section scale. I'm going to zoom back out again to talk about what I think is one of the most exciting developments in understanding the structure, and something that's been looked at with greater intensity over the last 5 to 10 years and is still wide open for major new contributions. And that is defining the full extent of the detachment system. Let's take a look at a map of the origin again. I showed you a very basic cross-section through the origin at the start of this talk, showing the South Tibetan Detachment System exposed at the crest of the origin and cutting through its highest peaks. However, you may have noticed from the map that there are many other contacts between the blue unit, the Tethyan Sedimentary Sequence, and the pink unit, the Greater Himalayan Sequence. I've put stars on some of these. They occur both in the up-dip direction, or foreland of the origin as Klippen, and in the down-dip, or hinterland direction as tectonic windows through the Tethyan Sedimentary Package that are collected.
Checking my Twitter notifications like a terrible person.
They occur both in the up-dip direction, or foreland of the origin.
Let me just kind of get my extended South Tibetan Detachment System. It leads up to above it is literally oceanic crust. Below it is Cenozoic granites. That makes sense. That's right after, right? Yep. Right after the supernova. Cenozoic granite. Greater, and like basically the peak of the mountains were induced by the energy flows resultant from the supernova of the Earth, and probably of this particle. Either this was the supernova, or I'm not quite sure exactly. Like the coordinate supernova. I think the core also supernova though, but like this was it must have been just a chain reaction of many things, because like Mount Grenard, Chicxulub, all these craters, also this. I don't think this is like the main event. I think that the Earth supernova was the main event of the process, the actual core, and it emitted Mount Grenard in the process, as well as causing another particle to really supernova, maybe something to do with also from pressure from the water, maybe, and from below, or I don't know. Essentially, I'm not exactly zeroed in on what happened, but this does make sense for a supernova of a particle to the north of its, but below the surface of the Earth.
And is Klippen. And in the down dip, or hinterland direction, is tectonic windows through the Tethyan Sedimentary Package that are collectively called the North Himalayan Gneiss Domes. Systematically, researchers have been investigating each of these occurrences, and in nearly every case, the contact is a tectonic one characterized by top to the north shear, in almost every way similar to the STDS, the South Tibetan Detachment System, that we have just gotten to know. So in cross-section, this is what that would look like. This cross-section is a generalization that incorporates geophysical constraints from the major in-depth geophysical profile of.
Every time, though, it just doesn't fucking make sense to me that they call it top to the north if it descends. It's like the descending. I don't like that they draw this line. I guess it's fine. Like there was a motion of the Indian basement when it could have just been maybe just a motion of above, but Not so much the Indian basements.
The late 1990s that passed through between Sikkim and Bhutan.
Maybe there's evidence, pardon me, if there's like substantial evidence for why they would show it on both sides and not just above, like, because some of them they don't show it like on both sides here.
So we did a long strike tour of the detachment system, but now let's take a look at some of the cross sections for different across strike positions of the South Tibetan Detachment System.
It's literally
and I've
waves.
indicated approximately where these might be located on that cross section above as 1, 2, 3, and 4. First, we see the South Tibetan Detachment System exposed in a clip in western Bhutan. Here, the shaded area around the dark line of the detachment surface represents a kilometer-thick ductal shear zone separating high-grade metamorphic rocks in the footwall, the Greater Himalayan sequence, from sedimentary rocks in the hanging wall, the Tethyan sedimentary sequence. We don't see a discrete detachment structure at the top. Moving towards the north in the across-strike direction, here's the Dhaulagiri cross-section that we saw previously. And in the Everest region, here again is the cross-section that we saw, showing clearly a two-structure system, that upper detachment structure being the Chomolungma detachment, which gently downcuts into the lower thick ductal shear zone called the Lhotse detachment, marked here.
Upper
is the lower STDS. And then finally, farthest north, a North Himalayan gneiss dome, the Kangmar dome in this case, with a thick top to the north shear zone separating underlying high-grade metamorphic rocks from overlying low-grade Tethyan sedimentary sequence rocks. The shear zone has been exhumed here by later ductal brittle, perhaps domal structures. Between these cross-sections, these four cross-sections, we're looking at more than 200 kilometers of a cross-strike exposure of this structure. There are no identified hanging wall or footwall cutoffs, making it tricky to quantify the amount of displacement. Yet we see similar metamorphic grades in footwall and hanging wall across this great distance. This was likely a subhorizontal structure as it formed. Now I'll talk a little bit about melt and the thermal evolution of the shear zone. And to inspire us is the Manaslu Pluton, one of several large granitic bodies situated at the top of the Greater Himalayan sequence, just beneath the South Tibetan Detachment. A common element in this talk examining the South Tibetan Detachment System has been the ever-present melt. Here we can see examples from Western and Central Himalaya of up to 100% melt pooling beneath the detachment. You'll recall the injection complex interacting with the Zanskar segment of the detachment system, drawn in the top left. In the top right is a photo from the Rongbuk Valley in the Everest region, and the bottom photo shows the Manaslu Luca granite sitting directly beneath the South Tibetan Detachment System and overlying Tethyan sedimentary rocks. There's only one documented case of Luca granite intruding into Tethyan rocks, the Buraburi granite in western Nepal, studied by Rodolfo Carosi and colleagues. The role of melt on the rheology of shear zone rocks is yet to be studied in detail, but this is certainly something that needs to be addressed in understanding this detachment system. And to drive that home, here are just a few more visuals of these major injection complexes in the Everest region and their proximity to the South Tibetan Detachment System. Related to partial melt and the high temperature, these major injection complexes in the Everest region and their proximity to the South Tibetan Detachment System. Related to partial melt and the high temperatures of metamorphism in the footwall of the South Tibetan Detachment System is the thermal evolution of the ductal shear zone. We certainly have cold rocks in the hanging wall. The Tethyan sedimentary sequence has barely reached 300 degrees Celsius. And we have hot rocks beneath, some coming up from granulate facies conditions during the Miocene. By looking at a number of temperature-sensitive chronometers, we can reconstruct the thermal evolution of tectonites in the shear zone. And what we find when we do that is that the shear zone was quite hot when it was active, and it very quickly cooled when shearing stopped. I'm showing here a data set from the Ductal South Tibetan Detachment System shear zone in Sikkim. You can see
I need to listen to that again.
tectonites in the shear zone. And what we find when we do that is that the shear zone was quite hot when it was active, and it very quickly cooled when shearing stopped. I'm showing here a data set from the Ductal
Like a
South Tibetan
supernova?
Detachment System shear zone in Sikkim. You can see the structural setting in the photograph at the bottom. The fault scarp of the upper discrete fault is shown in red, and the ductal shear zone in its footwall is shown in orange. And we're sitting here at the edge of the Tibetan Plateau. For the study, we dated zircon in syntectonic leucogranite dikes, with crystallization temperatures coming from titanium and zircon thermometry. We dated prograde and synkinematic monazite. We obtained argon-argon cooling ages for muscovite, apatite fission track ages, and uranium, thorium, helium ages for apatite. This combination of chronometers gives us temporal information over a temperature window of more than 700 degrees Celsius. In this example, on this temperature time plot, you can see that the shear zone was active from about 23 to 13 MA. And then it cooled from more than 700 degrees Celsius to less than 100 degrees Celsius in less than 2 million years. This thermal evolution must have had a profound effect on the heat budget.
I'm just writing down 35 to 23 MA, high temp, prograde, metamorphism. High temp, decompression. 23 to rapid cooling during late 14 to 12. Rapid cooling. Okay.
And the rheology of the origin. We've talked a lot about the South Tibetan Detachment System as a structure in isolation, but how does it fit into the evolution of the origin? Remember that this is not a structure our classical models of orogenesis would have predicted. I'm going to review the range of models or ideas that have been proposed for how it may have formed. The first ideas that were proposed about the formation of the detachment system focused on an extensional origin. This was before we had any timing relationships on the detachment or any information about how it might project at depth. And it was argued that the development of such a thick origin may have caused gravitational instability at the crest of the origin, locally rotating sigma 1 into a near vertical orientation to allow for low angle extensional slip. You'll recall that by 1992, we knew that the main central thrust and the South Tibetan Detachment System were likely active at the same time. This, combined with the pervasive deformation in the intervening Greater Himalayan Sequence metamorphic package, then led researchers to argue that these two structures formed a wedge around the metamorphic rocks, which have been ductally squeezed out between them. By the end of the 1990s, with the major in-depth geophysical profile results available and descriptions of the detachment system in the North Himalayan gneiss domes and in Klippen, it's become clear that the detachment likely does not project down to the main Himalayan thrust, the base of the orogenic wedge. Numerical models by the Beaumont and Jameson Working Group incorporated melt weakening of the Greater Himalayan sequence into numerical models to argue that the South Tibetan Detachment System is the upper boundary to a channel flow of weak metamorphic rocks. The interference of shear and pipe flow in the channel produced top to the south shear at the base analogous to the main central thrust, and top to the north shear at the top, forming the South Tibetan Detachment System. More recently, Alex Webb and colleagues have argued that the Greater Himalayan sequence has been constructed by basal accretion to the orogenic wedge, and the South Tibetan Detachment System formed a passive roof thrust to this developing duplex system. What's clear from all...
I think they might mean top to the south, top to the north by physically the top side of the fault line. The top side of the fault line is to the south. The bottom side is to the north.
All these models and this progression of thought is that this structure has challenged our conceptions of collisional orogenesis and will continue to do so into the future. When orogenic models are sufficiently well developed, they are predictive, and we can use our studies of the detachment system to test model predictions. Here's an example where I've tested the pressure, temperature, time path of a tectonite from a clip in Bhutan, the path shown in orange on the pressure temperature plot, against two different channel flow models in which particle paths were followed through the model, producing their own model pressure, temperature, time paths. In this way, I could show that not only is the final geometry of the model similar to the geological record in this region, so the structural cross-section of the model in the bottom right, but I could also show that the path and tempo of rocks through pressure temperature space was similar. In summary, I've covered for you why this low-angle, origin-parallel fault was an unexpected discovery in the Himalayan origin. In touring the origin, you've seen that it is large-scale and probably was sub-horizontal when it formed. Deformation was broadly coeval with the structurally lower, parallel, and opposing shear sense main central thrust, and deformation was in general melt present. Peak to post-peak shear resulted in a condensed upright metamorphic field gradient, and deformation occurred at fairly high temperature, though the shear zone cooled rapidly once it ceased. The structures played a critical role in orogenesis, in forming the Himalayan origin. Based on my own research findings, I currently favor the channel flow model as best explaining its formation.
Channel flow like carved by a supernova?
There are a number of outstanding questions about this detachment system that we're just beginning to scratch the surface on. How precisely can we pinpoint shear initiation, cessation, and duration? Was shear time transgressive? Did the active shear plane move up section or down section through time? Were all segments of the detachment system active at the same time? What is the across-strike continuity of the structure? What role did dynamic rheology play in allowing this detachment system to form? What role did changes to boundary conditions play? There are some future exciting research directions that I hope we'll see more of. We could look at pressure, temperature, time, deformation transects through the detachment system, perhaps at the level of detail that's been achieved for the main central thrust. We could focus on direct dating of the upper detachment structures, that brittle ductal structure preserved along the main crest of the origin. We can investigate the interplay between melt, fluids, and shear. Thank you very much for joining me in this presentation. I'll leave you with a list of all the citations that I used for those of you that want to dig deeper into this topic.
Okay, well, the Himalayas on the plus side are highly, highly researched, like compared to other places like Mount Gurnar. So that definitely was supernova worthy. I don't see any issues yet with the interpretation that there literally was mass of water sitting in this region that had moved in this direction and pressed down on a particle here that was physically unable to support the weight of because the particle was beneath the surface. It couldn't support the weight of the surface, the pressure, so it literally supernovaed. nothing in this presentation that doesn't really fit it so far that I haven't already accounted for, like radiometric dating being invalid as a method of absolute dating, but valid as a method of sequencing things, and that this was all much more rapid than is written of in other places and so on. Ignoring all those things. Nothing that's really, or including all those things, nothing that's counter to a supernova interpretation thus far, and in fact, pretty supportive of, I mean, the general trend of a low angle increase of these layers from the northern Tibetan region here. I'm not sure exactly what this region is called or considered, where Tibet ends. Tibet might end at there, I'm not sure. But where the shallogram opening is due to a vortex that then literally caused the particle to explode, I guess in this direction some reason. And through this layer, and I don't know, but doesn't seem impossible or counter, but supported instead by this first video. So that's my interpretation thus far. That's good. I'm glad I checked out this one, the South Tibetan Detachment System. It's kind of a boring sounding name. It's like, dude, the fuck's sake, it's like 2 tiers into the Himalayas. It's not just it's not the Himalayas. It's the South Detachment, Tibetan Detachment System. So it's a little specific, but it's definitely exactly what I was interested in, and that's why I watched it. And I'm glad they had this presentation, and hope that I could add some to the conversation of what's going on here, because I mean, just the concept of it being dendrites, of it being like numerically evenly divided, like literally divided into segments by fault lines that maybe point back in a general direction towards a point of origin of all of this, where the supernova actually emanated from, where the particle was that it supernovaed under the pressure of the weight of the world upon it, I guess. Alright. Peace out.